Okay, so welcome back. This is part 4 in our series where we show you how to program your electronic bench testing instruments. You can see here we've got an oscilloscope, signal generator, and we show you some of the basic procedures that should apply to any bench test instruments that you have connected via USB or your network, your Ethernet LAN. And here we've got an example of what we've been talking about in the previous videos. We got our computer, and we're sending a signal to our signal generator that varies the frequency of the sine wave coming out of the signal generator. And then it goes into this whatever device under test, or DUT, we have here. And we're applying a variable frequency sine wave to this device under test. And we are measuring the resultant output, the voltage waveform, on our oscilloscope. And this oscilloscope is internally measuring for us the peak-to-peak voltage coming out. We know what the input peak-to-peak voltage is and what the frequency is, and we're measuring the output peak-to-peak voltage. And that's coming back to our computer in our Visual Studio software, and it is generating what you see here on the top right, which is a frequency response. In other words, we know what the frequency of the sine wave we're applying, and coming out of the oscilloscope, we know what the voltage is. And we're plotting voltage on the vertical versus frequency on the horizontal. And here we're showing an example of a frequency response analysis if our device is a transformer. And this is a three-phase transformer. And again, we can use this technique on any type of device that we want to know how it responds to various frequencies. So what we're going to look at in this video is a very, very, very important aspect of this that people tend to gloss over, and it causes a whole lot of problems if you don't think about it. It's a very simple concept. You need to think about how this equipment is going to respond and allow for the fact that you can have some errors and unexpected results, and you need to check those to make sure you're getting good data. So in this video, we're going to talk about what I call data verification. And if you do any software programming, even simple programming where you have a user interface and the user enters any sort of data, you have to be aware that users and equipment and anything in the real world can have errors in it, and you need to look at those errors and filter them out and deal with them, or else you're going to get absolute nonsense coming out. So here we're going to look at some basic techniques on how to verify data when you're writing software and we're using this test equipment to make sure you don't have garbage data. So here is another graph of what we're doing. We've got our computer here using Visual Studio. We're going to use C#. You can use whatever language you want. And over the USB COM port, we are telling it, we're sending a string that says, okay, set your frequency at each step in the analysis, and every second or every 2 seconds, setting frequency, applying that to our device under test, and then measuring from the oscilloscope. And here we're reading over another USB connection what is the measured peak-to-peak voltage from the scope, and it's going to be a string like this. And then the C# or the Visual Studio application is going to take the frequency we sent and the read voltage and generate this waveform. In the real world, it's not quite that easy. And we're going to look at what can go wrong with this, and you really, really, really need to address it, or else it's going to drive you crazy. In the engineering world, you often will hear garbage in, garbage out. And what that means is if your input data that you use as input to whatever analysis you're going to do, if that input data is garbage, then your analysis is going to be working on garbage input, and it's going to give you garbage output. And in the engineering world, generally, if you've been an engineer like I have for any amount of time, you know that new engineers tend to make a mistake in this area, and they don't realize that they have to verify the input data or else they'll get garbage output. So they might do a study and say the output is, the answer is 25 billion. Well, no, the output can only go from 0 to 1, so how can you have an output of 25 billion? Well, they didn't think to verify the input data first before they did their output. In this case, we have equipment that has different characteristics, and you really need to understand the characteristics of the equipment if you want to make sure you don't have garbage in, garbage out. For example, in doing our frequency response analysis, you will see down here a string that I actually received. The string that I got from the scope was supposedly representing the peak-to-peak voltage, and said it was 1.96 e to the 138th power, which means it was 196 gazillion volts, right? So clearly that's wrong. And if you're going to let that data go through in your analysis, you're going to get garbage output. So we're going to look at techniques to verify that data to make sure that it's not garbage. So the first thing you want to do is say, okay, what are the possible sources of errors in this system? Well, there could be an error in parsing the string we get from the oscilloscope. For example, it should be, in our case, something that looks like this, 2.1 times 10 to the 1, or 2.1 times 10, or 21 volts, it should be. So we got to make sure that it's going to look like that. Maybe we did a parsing error, but we have to make sure we catch that before we do our analysis. So it could be a parsing error, or it could be a timing or other issue resulting in either signal generator or scope or whatever equipment not being in a settled state prior to reading. It's not ready to give you an answer, so you have to make sure that the scope or the equipment is ready to respond. So parsing errors, timing errors, and the big one that people don't want to admit to is incorrect user code. So guaranteed, if you've done any software development, you know that you make errors. And the more novice you are, the more errors you're going to make. And you need to, at each step, make sure that any errors are caught, even code errors that you have made. Now, another thing we talked about in this series is the characteristics of the oscilloscope. If the waveform shown on the scope is either clipped or too small to read, you're going to get garbage data. So for example, here I've got an example of a voltage we're reading, but you can see it's clipped. It's supposed to be a sine wave, but it's going off the scale, and the peak-to-peak voltage being read is some garbage number. It's just a bunch of asterisks. Now, the other problem is I've got a 2 point something volt signal, but the scale on the scope is too high to recognize that very small waveform peak-to-peak voltage. And in fact, it's telling us it's 12 volts when actually it's 2 point something because it doesn't have enough waveform to read, right? So it's these kind of things that you need to be very wary of and make sure that you understand how your equipment works and that you are using techniques to verify your data. Here's some rules we can use, and depending on what you're doing, you're going to use your own rules, but this is to give you an idea about how you can apply some rules to make sure you have legitimate data. Our signal generator has a maximum peak-to-peak voltage of 20 volts. That's the limitation of the signal generator. So what we can do is we can say if the maximum peak-to-peak voltage from the signal generator is 20 volts, then any measured volts we're getting from the scope obviously should be less than or equal to 20 volts, right? If you can only output 20 volts, probably you're only going to get results that are 20 volts or less. Now, you may have some amplification, but you got to be knowledgeable about the characteristics of your devices and your circuit. So that could be a rule that we can apply. Say, hey, we're not going to accept any voltage that's outside the range of the signal generator can produce. Also, each measured value shouldn't be very different from the previous reading. Again, that's going to vary depending on how you're implementing this, but you got to make sure that if you have a reading of 2 volts and then the next reading a second later is 3,421 volts, probably there's an error right there, right? So you got to make sure that you're not having big variations between readings. And very importantly, this requires that you have a previous reading to check against. So for example, if your first reading coming off the scope is 25, you don't have a previous reading to check because that's the first reading. So you're going to have to add some logic to say, well, are there previous readings? I'm not going to check against the previous reading if there's no previous reading. Also, you need to provide in any software user feedback and error checking, all right? Make sure that you are telling yourself as the software is running, giving yourself feedback about what's going on, what are the values, so you can visually see what's going on and if there are some obvious errors, and include in that some error checking that you can say, hey, we've got an error, and give that feedback to the user. Also, one of the most important things is never assume, always verify. Never assume your code is right. Never assume the operation of the oscilloscope or the signal generator or whatever equipment is correct. Always verify that what you're doing, you always need to know every step of the way. So as we said, in checking reading deviations from the previous, you need to include logic to make sure you have a valid previous reading. Very important. Also, what do you do with bad readings? So let's say you've got one reading of 2 volts and the next reading is 3,526. What are you going to do with that 3,526 reading? If you discard the bad reading, you need to make sure your ranges are valid and consistent. You don't want to just get rid of a reading. You want to think about what's going to happen to your lists or your arrays or whatever if you just get rid of that reading. So you got to be aware, don't just get rid of bad readings. Make sure you know what's going on with your code. So some possible solutions. In our solution, we can limit to only a 0 to 20 volt range and replace the latest reading with a previous reading. So for example, if my first reading is 2.1, the second reading is 3,526, you know the 3,526 is bad, so you can say, well, I'll just replace that with 2.1, the previous reading, and move on. Since you don't have a good reading, you got to come up with something, so you can just use the previous. That does keep you from having wild readings like 1.2 times 10 to the 16th or whatever. Is it ideal? Maybe, maybe not, but it's one option. You could also do what we've talked about in other videos on this channel in data acquisition called low-pass filtering. And what that does is it's some code where you take only, say, 20% of the latest reading and 80% of the previous reading and add them together to get 100%. So let's say I've got one reading of 2.1 and the second is 3.5. I'm not going to totally trust the 3.5. I'm going to take only 20% of that latest reading and 80% of the previous reading. That's kind of like a low-pass filter, but it's saying I'm going to be careful about latest readings and filter out any big movements. Now, the problem is if the latest reading is one huge number and the previous is, say, 2.3, you're still going to get a bad result. So you're going to have to look at multiple solutions like limit to just 0 to 20 volts and maybe do some filtering. Another way, instead of filtering, is allow only a 60% change from one reading to another. If reading 2 is within 60% of reading 1, it's okay. Otherwise, you're going to just take the previous reading. So there's a bunch of different ways that you can filter out the data to get rid of bad readings. And again, if the latest reading is much different from the previous, replace the latest with the previous. So there's a bunch of different ways you can handle this. So now here's our application we have so far where we're doing a frequency response. And here is just one example where I've got a band pass filter that I built on the bench, and we'll show that in the future. And it's got a center frequency around 150 kilohertz, and you can see a bandwidth like this. And what we're going to do is we're going to take some of the data verification tools we just talked about and implement that in our application. And we're also going to modify our application so we can do what you see here. And this is our application with the additional ability of being able to run multiple scans. And in this case, we've got 2 results plotted on the same frequency response graph for our power transformer, our 117 volt to 12 volt transformer. And the blue here, we've got the transformer just operating normally. And in orange, we have it with a short-circuited secondary winding. You can see the different frequency response. And we're going to show you how to modify the code so that we can do one scan, modify our circuit, modify our transformer in this case, and then do a rescan and overplot the different response on the chart. So that'll be coming in the next videos. If you like any of these videos, I encourage you to hit the like button, subscribe, hit the bell notifications, and most of all, please let others know that we're here so we get some views. Really appreciate it. Otherwise, take care. Have a really good day. Thanks.